Welcome back everyone, my name is Pedram and this is where we do advanced time series analysis, deep forecasting. Alright, so module 3, part 1, exponential smoothing methods. So method simply means that these are going to give us point forecast, not prediction intervals. So we're going to look into the details of all these methodologies, and the mathematics might become a little overwhelming for many of you guys. So don't worry too much, as long as you get the gist of it, you get the high level understanding of what are these methods, how do they work, when should you apply which of them to your time series and things like that, you're good to go. So I think this is one of the most important slides that I'm going to give you a high level summary for the entire exponential smoothing methods, right? So if you're on board with me on this slide, and then you should be good to go. Again, don't worry about the forecasting equation. We're going to look into all these things later on, but as long as you get the gist of it, I think I'm okay with that. All right, so remember, this is our classical time series approach, and we're looking into our first family of model, which is exponential smoothing, right? We said in module 1, these are decomposition-based models. So basically, it means that we are going to look at the time series, decompose it into its components. Is it trend? Is it cyclicality? Is it seasonality? Whatever it is. And we're going to use some simple weighted averages. We call them exponential smoothing methods to model those components, right? So imagine I have a time series, I break it down into a bunch of components, and I model each components using an exponential smoothing method. So that's basically at the core of what we're going to do. Now let's look at the most commonly used methods. I have the name of the method on the left. So we have SES, which stands for simple exponential smoothing. We have Holt Linear trend. We have damped trend. We have Holt Winter, and we have Holt Winter damped trend, right? So, and this is what kind of data pattern is suitable for that? Well, actually, if the data pattern is like this, what methodology is suitable to this data pattern, right? So let's start with the very first one. I'm going to label it as number 1, and let's try to make it as color-coded as possible. So number 1, and we say that if the data pattern is showing no trend or no seasonality. So what is the example? So for example, we can think of export level in terms of percentage of GDP, right? So the export in terms of percentage of GDP, I don't know, it can fluctuate. It can go up, it can come down, it can go up. We have something like this. And as you can see, there's no clear trend here. And imagine this is our terminal time T. And there's no clear trend, there's no seasonality. And SES is basically a simple exponential smoothing method. So as a benchmark, let me remind you what was our naive forecaster and what was our mean forecaster or average forecaster, the two extremes, right? So maybe you should pause the video and then think about that. So pause the video and tell me what is your naive forecaster into the future and what is your simple average into the future, right? Or grand mean benchmark into the future. All right, so the naive forecaster is going to be something like this, right? Again, it's independent of your time horizon. We say this is your naive, if you want to forecast into the future. And your simple average is going to be, I'm going to look at the entire data set, take a simple average. Let's say the average is here. So we can call it grand mean or average, whatever. So this is your average. And your SES, simple exponential smoothing, is going to be somewhere in between. SES, right? Somewhere in between the two extremes, right? The equally weighted and all the weights going to the past observation. So SES is going to be somewhere in between. And if you look at the forecast equation, again, don't worry about the details. Just follow me at the high level. It says that the forecasting equation is just a function of previous level. This is L stands for level. So level. Basically, what we're trying to get out of this train set is that give me a level, and I'm going to use that level for my forecast into the future. So this is what SES is going to use, right? And obviously you can see this is a good fit when there's no trend or no seasonality, because if there's a trend, obviously it's not going to work, right? So that was number 1. So this is our number 1. Let's do Holt linear trend. So we say there's a linear trend somewhere. So imagine you are looking at, I don't know, maybe the GDP per capita in US. If you look at that, it goes, it's basically a straight line up. In recessions, it get a dip and then it goes up again. So this is your GDP. So we can say GDP per capita, and this is over time. And now, obviously, here, if I use SES, that's nonsense, right? The SES is going to give me, I don't know, maybe something like this. So this doesn't make any sense. So you need a model that when it's projecting into the future, it's appreciating that trend, right? So your data is showing trend, but no seasonality, right? So what do we do? We are going to say, let's use Holt Linear trend, and that model is going to make a prediction like this. So this is going to be your Holt Linear trend. Okay, and as you can see now in the forecasting equation, what do we have? No, let me actually say this is number 2. Again, I told you I try to be color coded as much as possible. So in our forecasting equation, now we have 2 components. You know, the forecast into the future is not only a function of level, it's a function of a slope as well, right? And that depends on how many time horizon into the future you're looking into, right? So this should be pretty straightforward. Now we have a combination of level and trend, right? Okay, now the next one, let's use another color, 3, damped trend, right? So the idea of adding the damped version of trend is that especially for the time series that you assume that you're making some assumption for the growth of the time series into the future. But it makes perfect sense that the growth is not infinitely linear into the future, right? You know, imagine you're talking about the growth of a company. Yeah, in the first years, it might be 5%, 10%, and it accelerate to 20%. But eventually, when the company matures, that growth rate is going to plateau, right? So even for the GDP per capita, if you want to assume that this thing is not going to go in a straight line, if you want to damp it like this, you're assuming there's some cap in the growth, right? So if you want to do something like that, you will be using your damped trend, right? So again, this makes sense for the processes that you assume there's a cap or there's a floor for your growth, right? The growth can be positive or negative, right? For example, for population, you know, if you want to look at the population data set, obviously this 3 makes a lot more sense because going into the infinity, the population growth cannot be just a straight line upward, right? Yeah, because the structure in the time series is going to change. Now, let's do number 4, which is Holt Winter. Holt Winter comes to place where we have some seasonality, right? So like our airline passenger data, the airline passenger data is seasonal, and as you can see, it both has a trend and a seasonality, right? When it has a trend and seasonality, we need to come up with a model that appreciates those 2 components, right? We need to come up with a model that say, hey, I have a level component, I have a trend component, and I have a seasonality component. Don't worry about these 2 formulas. One of them is additive, one of them is multiplicative, but for now, let's say we are adding seasonality, right? So then your Holt Winter is going to become something like this. I don't know, we're projecting into the future, right? Obviously, the magnitude of seasonality is larger, but you get the idea. So for this one, obviously SES doesn't make any sense. This is your SES. Your Holt Linear trend is going to miss. This is your Holt Linear is going to miss the seasonality, and obviously the answer is going to be number 5, Holt Winter. So this is your Holt Winter. And by the way, I forgot to say that when we get to the damp trend, this one, look how we are damping that trend. That trend used to be a linear function of h when we use linear. Now we are using it. This is a damping function, which is a function of h as well. As h increase, because these phi's are less than 1, then this number is going to increase at a decreasing rate, right? So this is what is generating this kind of behavior. This kind of behavior, not this. Okay. All right, and then lastly, it's a combination of all of the above, right? So let's call it number 6. And both it has a damped trend and seasonality. And whatever your data set is, you assume that there is seasonality, but you think that the trend is not going to go into the future just linearly. So you're going to appreciate the seasonality, but at the same time, you will damp that trend. So if that makes sense. As you see, this is upward sloping, but at a decreasing rate, but it's also appreciating your seasonality as well. So, and again, this is how we're going to add it. We have a level component, we have a trend component, we have seasonality component, and we are damping those trends. So if you followed along with this slide, I think you're good to go. This is the gist and the core of the rest of the slides that I'm going to cover. So again, in the future slides, you might get a little overwhelmed with the formulas, but always remind yourself that this is what I need to know and I'm good to go. And later on, when you're doing a Python version, of course, for Python, you're not going to use the formulas at all. But now, at least in Python, when you put trend is equal to additive or seasonality is multiplicative, you know what does that mean, right? So basically, you're going to create one of these combinations in Python. So that's what I want you to take away. All right, so let's start with our first method, which is simple exponential smoothing, right? So as I said earlier, SES is suitable for forecasting data with no clear trend or seasonal pattern. Here's an example. And remember, we are going to predict just one level, and that's what we're going to use for projections into the future. So our naive forecaster is going to, we said it's something between naive and mean, right? So naive forecaster is going to give all the weights to the last observation. So this is what the naive is going to do. Our simple mean forecast, think of it as benchmark, is going to give weights equally to all observations in the trained set. So basically all the observations in the trained set. And I don't know, I'm just hypothetically making some numbers. So maybe this is your mean. And then obviously our SES is somewhere in between, right? So it's going to be, I don't know, I'm just making up these things, SES, but we know that it's somewhere in between, right? Your goal is to find that level, right? So that's why in the forecasting equation, we only had one thing, which was level independent of H. And this is how it's doing it, right? This is a formula. And as you can see, it's a weighted average of YT minus 1, YT minus 2, and etc., right? And this alpha is our smooth, basically this is our smoothing parameter. So alpha can be anything. For example, if it is 0.5, then what do we get? If it is 0.5, you know, the first weight is going to be 0.5. The second weight is 0.5 multiply 1 minus 0.5, which is 0.25. The third one is going to be 0.125. That's where the name exponential is coming. As you can see, the weight is decreasing exponentially, right? The next one is 0.5 multiply 1.5, right? It's going to be a lot smaller. And yeah, so if this alpha is large, so if alpha, for example, if alpha is exactly equal to 1, what will happen? So you'll get your naive forecaster. Everything is going to be reflected in the last observation. And obviously we cannot set alpha is equal to 0 because that's nonsense. You're going to get 0, so your projections are going to be equal to 0. So this means that we are going to put a boundary for alpha. Alpha is going to be between 0 and 1. All right. So here are the SES weights in closer look. So I'm going to use the same formula. Again, this is a simple weighted average. We are putting more weights on the last observations, right? And this is our alpha, right? We said alpha is between 0 and 1. This is our smoothing parameter. For any alpha between 0 and 1, the weights attached to the observation decrease exponentially as we go back in time, right? So that's where the name exponential smoothing is coming from. And some of the weights are going to be roughly equal to 1. And this is simple, you know, we are looking at historical data. This is observation number 1, 2, 3, 4, 5, 6. No, you can start from 0 or 1. It really doesn't matter. So this is the last observation. That's the point. We're going to give more weights to last observation. So for different values of alpha, obviously we're going to see. So let me actually write something down. If alpha increase, we're going to have faster decay. And this is what I'm trying to show here in this table, right? If an alpha is equal to 0.2, then let's say last observation has 20%, the one before 16%, the one before 12%, all the way to this one, which is 6.5%, right? If I look at alpha is equal to 0.8, last one, 80%, the one before 16%, and if I look at just 6 observations before, it's almost nothing, right? So now you see how this smoothing parameter is changing the weights in your exponential weighted moving average, right? At the end of the day, guys, remember this SES is trying to find the average value that your data is fluctuating over, right? So if your data is fluctuating over some average, so it's trying to find that level. So that level is going to be your forecast into the future. Obviously, again, I'm just repeating myself, but it doesn't hurt. So obviously, if you have a data like this is nonsense. You should not use SES. Okay. All right. Okay, now let's see what are the equivalent forms for a simple SES method, right? So here at the top, I'm going to remind you what are we doing for our forecast. So we can say y hat, and let's look at the forecast into the future. T plus h given t. We said it's the weighted average of previous observation plus alpha multiply 1 minus alpha yt minus 1 plus, let me actually write it for one more term because we need it. 1 minus alpha to the power of 2 yt minus 2 and etc. Okay, so I'm going to do a little bit of mathematical tricks here. So nothing fancy. I'm going to say, okay, it's equal to alpha yt, and then I'm going to factor in 1 minus alpha, right? So if I factor in 1 minus alpha from this and 1 minus alpha from that, what do we get? We get alpha yt minus 1 plus alpha multiply 1 minus alpha yt minus 2. Hopefully it makes sense. Okay, now I want you to pause the video and think about this term. What is this? Yeah, so this is the predictions for the last period. So this is your y hat t, and basically given, well, this is one period before, right? Given t minus 1, right? So that's basically, yeah, what we were doing. And to make sure that it's not confusing, our h here is equal to 1. Okay, so this is t plus 1. So that's why we get the previous projections was y hat t, right? Now I can write it like this. So this is going to narrow down to something like this. Y hat t plus 1 given t is equal to alpha yt plus 1 minus alpha y hat t, and in the previous period given t minus 1, right? So again, there's nothing special, nothing fancy here. We just reformulate what we had, right? So we are going to call this version form, we call it weighted average form. So I think the interpretation is more important. Just try to get that part. So what is the weighted average form of SES? It says that your forecast is basically a weighted average between the most recent observation and the previous forecast. So this is a forecast. This is real observation. Last observation. This is also a forecast in the previous time step, right? So this is, we call it weighted average form. Now we can show it in component forms as well, because remember guys, these methods and models, they are decomposition based models. So let's break it down into its components and use exponential smoothing methods to model those components, right? So that's exactly what we're doing. So the component we say for simple SES, simple exponential smoothing, the only component that we have is a level, because remember at the end of the day, what you care is just a simple level. So give me that level. What is that level? Okay, level T. So there are two equations here. One is the forecasting equation. One is a smoothing equation. The forecasting equations are the one that I showed you in the very first slide when we were summarizing all these methods. It's very straightforward. It says that your predictions is simply a function of level at time t, right? So remember, if I want to remind you, we had fitted values versus projections into the future. So we are going to use the same formula for fitted values. I'm going to say y hat t, because at each point, what are the fitted values? So this is going to be equal lt minus 1. So we need that. So at each point in the train set, this level might be different. However, for projections, so let's call it fitted values. You can think of it as train set. And then, however, for forecast into the future, what do we get? We have y hat capital letter T, because we are at the very last time step, given T is equal to LT. And this thing, I want you to pay very good attention. This is a little confusing, but just bear with me. Do you see that the fitted values is a function of a small letter t? So if you're at time step 10, it's going to be L9. If you're at time step 20, it's going to be L19, right? However, for forecasts, This is the very last time steps. If your capital letter T is fixed and that number is equal to 20, that's going to be 20. So if you want to forecast 1 step into the future, that's L20. 10 step into the future, L20. 100 step into the future, L20. So that's why in the we're gonna see the next slide. In train set, your model is gonna make a prediction like this. The level is gonna change. Depending on your alpha, this is going to change differently. So this is your fitted values. And now let me use another color. This is your forecast into the future. Hopefully that makes sense. Why in the train set these fitted values are changing, because there's a level historically. But projecting into the future, it's not that doesn't depend on the H. All right. And our smoothing equation is now simply this. LT is equal to alpha yt and 1 minus alpha lt minus 1. So this is it's coming from this weighted average form, right? Look at that. Now we say, hey, what you wanted to predict with SES is a level. That level is the weighted average of the past observation and the previous level. That's simple. So these are all connected, right? Don't try to memorize one versus the other one. Again, understand them at a high level, and then hopefully this visualization helps you to understand why the fitted values are going to change over time, but the forecast values are going to be independent of H. So we're using the same formula. Okay, so here I summarize what I said in the previous slide, SES fitted values versus forecast, right? So for fitted values, we're going to use this formula, and then for forecast, we're going to do this one, right? And as you can see, at each point in time, the predictions, the fitted values is the same as the previous level, and we know that previous level is going to change in the train set. For forecasts into the future, all those forecasts are going to be flat forecasts, right? So because look at that, this thing does not depend on H. If H equal to 2, we get the same number. 3, same number. 4, the same number, okay? All right, so all forecasts take the same value equal to the last level components. And remember, this method only works when your data shows no trend and no seasonal component. I know I'm repeating myself a lot, but as I said, it really doesn't hurt. So this is going to be your LT. All right, okay. So let's look at an example. So this example hopefully is going to clear out any last uncertainty or doubts that you have in mind. So we're gonna work with a very simple numerical example and see how this SES is projecting into the future and what are the fitted values, right? So let's say we have a time series starting from 1960. Remember, your timestamp starts from 1, not 0. So we'll see why we need this 0 later on. But your time starts from time step 1 all the way to, I don't know, whatever that number is. These are projections. H is your forecasting horizon, and this is 5 years after 2017, which is 2022, right? So this part is going to be your train. This is what you're going to make a forecast, and you can think of it as a test set, and you can think of it as forecast horizon and whatever, right? So now let's see let me actually show you on the graph, and then I'm going to hide the graph and tell you where the numbers are coming from, right? And basically right now we want to estimate, we want to identify the parameters of an SES model, right? So I will see what are those parameters and then how we can identify them, right? So let's start again, and just as a reminder, this is your fitted values. These are your forecasts into the future. So this is Algerian export of goods and services in terms of percentage of GDP. This is something that doesn't have a trend or seasonality. And for that, we are using something like this. And we are plotting it for different values of alpha. And by the way, these some of the tables and charts that I'm using comes from the main textbook of the course for the econometric section. So check out the resources by the end of this video, and then hopefully you should be able to find that. Okay, so for different values of alpha, of course, we're going to see different SES, right? If alpha is equal to 0, we never set it to 0. It's nonsense. It's going to predict 0 all the time, right? So this doesn't make any sense. And but for if alpha is equal to 1, this is basically your naive forecaster. And as you see, the naive forecaster is just 1 step ahead forecast in the train set. And let's say here, naive forecaster is, I don't know, something like this. Oops. And then if I use different values of alpha, I get this one as SES. And there's a little shift in this forecast in the train set as well. Now let's see where these numbers are coming from. For example, how did we get this number? Okay, so I'm gonna write some notes here on this slide and maybe next slide. Actually, you know what? Let's try to do it here. Let's try to do it here. So I'm gonna start from some assumptions. So we say alpha is equal to 0.84. This is the initial value. And level 0, don't worry about it right now. For now, we're going to say it's 39.54. Basically, your algorithm, if you want to think of it computationally, you can start from any random number. This is your initialization number, right? So alpha can be 0.5, L0 can be, frankly speaking, 10 or 100, whatever. Later on, we're going to optimize these values, right? So these are the optimized values for alpha and L0, right? So I have alpha and L0. So this is it's going to be my L0, 39.54. This is given. Okay, we start from something, we optimize it. So let's say initial value, initially given, right? And yeah, and then what do we need? So basically, at the end of the day, if you want to identify the parameters of this model, so SES has two simple parameters, right? So the parameters of SES model is alpha and level 0. You have to have a cost function or loss function, right? So what is your loss function? As always in regression, we can think of SSE, right? Sum of square of errors. So basically, if I can find those errors, right, I can call them E, no summation, t to the power of 2, when t goes, well, let's do I. You get the idea. I goes from 1 to capital letter T. And then this is mean sum of square of errors, or sum of squared errors. And I want to minimize it over two parameters. The parameters are alpha and L0. Okay. So what does that mean? It means that you need to have those errors. So what is error 1? Error 1 is going to be y1 minus y hat 1. Does that make sense? Okay. So what is y1? So y1 is actual data. So let's find the y1. 39.04. 39.04. Minus y hat 1. So do we have this one? No. So we have to use our equation here, right? So these are the fitted values. Remember, guys, we are in the train set. We're looking at the fitted values. So it seems that my y hat 1 is going to be equal to what? Y hat 1 is going to be equal to L0. Very good. And we have a number for L0. L0 was 39.54. And guys, remember, you can start from any number. L0, this is a computational process. You can do 20, you can do 10. This one that you're seeing here, these are the optimized value that these numbers are, that you see in the table are generated using that number. It's optimized, right? So now this means that my epsilon, my E1 or error 1 is going to be 39.04 minus 39.45, which is, what is it? What do we get? Well, is it 04? Yeah, I think it should be 54. Yeah, L0 is 54. Sorry, 39.54. So now we have 39.54. So we get minus 0.5. So this is your error number 1. Let me use my highlighter, and again, try my best to color code these things. So this is my minus 0.5, and I can show it here, right? Your actuals, the black line is 0.5 number greater, larger, oh sorry, smaller than the blue line here, right? So that's what we're doing. Okay, so this is your E1. We have to do the same for E2, E3, E4, and etc., right? So what is E2? Let me use my... So this is a very good exercise. I really want you to pause the video and do that because we want to see how we get these numbers, right? So, by the way, our y hat 1 was 39.54. This is, remember, the fitted values in the train set are basically simply previous levels. Look at that, etc., right? Okay, so E2 is y2 minus y hat 2. So do I have y2? Yes, y2 is equal to 46.24. Do I have y hat 2? So here, let me use another color to just make sure you don't confuse these things. So y hat 2 is equal to what? Is equal to L1. But do I have the L1? The answer is no, because you need to calculate it. What is L1? your L1 is basically, remember, I'm using the smoothing equation for L, right? I wish I could go back to the previous slide, but you get the idea. So you pause the video, go back to the previous slide and see what was the formula for L1, right? So basically L1 was alpha y1 plus 1 minus alpha, and this is your L0, right? L0, I have it, which is 39, where is it? 39.54. Alpha, I have it, is 0.84. If you plug those numbers, your level 1 is going to become 39. Again, I want you to pause the video and do that. 0.12. Okay? This is my 39.12 for L2. And I'm going to use that one as a projections for the next period, 39.12 for y hat 3. Okay? So hopefully you're able to back out all these numbers, right? So for fitted values, and we're using this formula for fitted values. Now for projections into the future, we know that it's independent of the age, right? So where's this number coming from? So we can also calculate that one. So we say we want to project into the future. So y hat of t plus h. Our t is 2017 plus 1 step ahead forecast. So I'm using this formula, guys. Given 2017 data, I'm not writing that thing, is equal to what? Is equal to y, well actually is equal to level in 2017. Are you following? So what is the level in 2017? It's this one. Oops, sorry. So let's use a highlighter. So the level in 2000, oops, let me see if I can use a right highlighter. The level in 2017 is this. I'm going to use that value for all the projections into the future. Oops, let's do it black. And as you can see, all these numbers are the same. So this means that your y hat 2017 plus 2 is equal to y hat 2017 plus 3, and etc. They're all the same. So that's why you see one number for all the forecast, but different numbers for fitted values, right? And again, if this seems too much, don't worry about it, but I just wanted you to see the mechanics and work with these numerical examples for the simplest one. And now we're going to expand this simple exponential smoothing, add different components, add actually second smoothing equation, third smoothing equation, and see how it works. But in order to identify, let's go back to the identification problem, guys. So we're using the train set, calculating these errors, error 1, error 2, error 3, all the way to error 58. And I'm going to sum them, error 1 to the power of 2, error 2 to the power of 2, all the way to error, in this example, 58 to the power of 2. I'm going to sum them and minimize them. And I minimize them over initial value of L0 and alpha. Again, computationally, your computer can start from any random initial value. So for example, you start from L0 is equal to 10, alpha is equal to 0.5. But because we're minimizing this cost function, you can use a minimization optimization technique, and then it's going to give you the optimal values. The optimal values are going to be alpha star and L0 star. Your alpha star is going to become 0.84, L0 star is going to become 39.54. Hopefully that makes sense. Hopefully it helps you to solidify what is the mechanics behind all these methodologies. And now for the rest of the slide, I will just show you the equation, and you can go ahead and give it a try. Try to back out those numbers for Holt Linear method, or if you really are interested, you can back out those numbers for Holt Winter method. Again, the calculation is going to be a lot more involved, but that's not the point. The point is that to understand how these things are working at the high level, why in the train set your predictions are changing over time, why in the test set your projections are flat. All right, now let's move on to our second method, which is exponential smoothing methods with trend. All right, Holt's linear trend method. So back in 1956, Holt extended the SES method to allow forecasting of data with a trend, right? So this model is suitable for forecasting data when there's a clear trend and no seasonality. Look at that. This is clear trend. We're talking about Australian population and with no seasonality. Obviously, it doesn't make any sense to use SES model because the projections are not going to be good. This method involves a forecast equation and two smoothing equations. Let me actually show it to you and then talk about it. So there are two smoothing equations. So that's why sometimes people call it double exponential smoothing methods, right? So we have simple exponential smoothing method, which we call it SES, and now this one double exponential smoothing method, or we can call it Holt's linear trend. Basically, those two components are level components. We have a level equation and we have a trend equation. Okay. So the forecast equation is pretty straightforward. It says that your forecasted values are basically whatever the level is plus h multiply whatever your trend component is, right? This h can be 1, 2, 3, and as you see, as we go further down the road, we have to multiply a larger number to the slope, so we get a larger values, right? So that's why what it can produce something like this. Okay. What is a level equation? So both level and trend equation, it's basically, these are simple weighted averages, right? A level equation is a weighted between this observation and previous level plus trend. Trend is weighted between this slope and previous trend, right? So again, this is pretty straightforward. Let me try to talk about well, look at this one. Guys, remember, this is going to be your previous level, and then what is that one? If I set h is equal to 1, what do I get? I get basically level t minus 1 plus b t minus 1. So this is where it's coming from. Again, it's a simple weighted average of your actuals and previous forecast, right? This is your previous forecast. This is your y hat t minus 1. Okay. All right. So, and then what is this one? Where's the slope coming from? So let me actually show you two random levels here. Let's say this is level t, this is level t minus 1, and this is your slope. So what is the slope? Slope is going to be, so let's call it slope. It's pretty straightforward. LT minus LT minus 1 divided by the base. What is base here? Let's say we go from HT minus 1 to HT. So it's going to be HT minus HT minus 1. But what is HT minus HT minus 1? Oh, this is going to be equal to 1 because there's one time step between the two. So that's where the slope is coming from. So again, this should be pretty straightforward. And now let's look at these bullet points. L shows the estimate of the level, B shows the estimate of the trend, and then alpha and beta stars are the smoothing parameters for level and trend. Don't worry about this star thing, in the textbook it talks about it, but this is just a Greek letter. We just want to make sure that this beta is different from beta in ETS model, so that's why we call one of them beta star, the other one beta. And again, honestly, this is just coefficient. It can be any Greek letter. Okay, so what are the parameters of this method, right? So for this method, we have to figure out what is L0. We have to figure out what is your trend 0. We have to also figure out what is alpha and beta star. So now this model has 4 parameters. The SES had 2 parameters. This one has 4 parameters. Okay, now let's look at an example from the textbook and see numerically how we can back out those numbers. So I'm going to leave this as exercise. For those of you who are interested in the details of these models, I highly encourage you to replicate these tables. This is exactly something we did. We did something exactly like this for the SES, and I want you to pause the video and do the exact same exercise for your Holt's linear method. So we know that the forecasts are not going to be flat anymore. They're trending because we're adding this component, which is function of h, right? And so that means that we're going to have something like this. So the forecasts are going to be something like this. This is great. And then the h step ahead forecast is equal to the last estimate level plus h multiply the last estimate trend. So we actually, this is for the level, and then the forecasts are linear function of h, right? So let me actually show you that table. And then again, leave it as exercise for you to back out all these numbers. What I want you to back out is basically a couple of things. So first of all, this is again our train set. So we have to use the fitted values formula. So fitted values. And for fitted values, what do? We say y hat t is equal to lt minus 1 plus, because h is equal to 1, so it's bt minus 1. So this is going to be your fitted values, and these are your projections, forecast. For forecast, obviously, you're going to use that formula, y hat t plus h is equal to level t plus h bt. Okay, And as you can see, this is different from SES. In SES, these were flat numbers. Now this is increasing, right? So this is what I want you to literally back out the first number, how we can calculate this. Where is it coming from? So you need some information. So you need the initial values. Actually, I'm going to give you the optimal values for you to use the formulas and back out those numbers. So the optimal values that you need, alpha is going to be equal 0.999. Your beta star is going to be equal 0.3267. Guys, this is a really interesting exercise. I absolutely encourage you to do that. L0 is 1005 and your B0 is 0.22. So just use these numbers and try to replicate. Remember, just like SES, the way that we do. Start from your error 1 was y1 minus y hat 1, and then do error 2, y2 minus y hat 2. And then along the way, you're going to figure out, okay, what is y hat 2? You have to use a formula. What is y hat 1? So hopefully you can back out all these numbers. First of all, again, this is your initial value for level, 1005, initial value for slope. And yeah, and alpha and beta stars, I just gave it to you. Okay, so after we have these epsilons, we're going to do the same thing, minimizing sum of square of errors over those 4 parameters, alpha, beta, again, star, not a star, really doesn't matter, L0, B0, B0. So this is what we're going to do. Cool. All right, hopefully you were able to back out those numbers in the previous table, and now you're ready to extend the model to the damped version of that, right? So to forecast, the forecast generated by Holt Linear method display a constant trend. Oops, let me see. There's a constant trend. That trend can be increasing or decreasing depending on the sign of B, right? And so this is your Holt Linear method. But empirical evidence show that these methods tend to over-forecast or sometimes under-forecast, especially for longer forecast horizons. Guys, remember, imagine we have something like this, population growth. We know that if you want to project it into the infinity, it doesn't make any sense to increase linearly. You want to get something like this. So let's damp that trend. Let's damp this number. Okay, so that's exactly what we're going to do. So we want to take this one and make something like this, right? So basically, and now we'll see the mechanics, how it works and why the coefficients are damped as we increase the h, right? Gardner-McKenzie introduced a parameter that damped the trend to a flat line sometime in the future, right? So this phi is going to be between 0 and 1. So this is damping parameter. And then it's going to be, again, it's going to approximate to a flat line, right? And that makes sense because growth cannot be flat into the infinity. So that phi is going to damp the trend so that it produces a constant sometime in the future. So this means that short-term forecasts are trended. Look at that, short-term forecasts are trended upward. Longer-term forecasts are going to be flat. Okay, all right, but how is it doing it? So let me actually show you 3 time steps. So for example, your h is equal to, let's do it this way. H is equal to 1, h is equal to 2, h is equal to 3, and etc. Okay. And for simplicity, I'm using, I'm using phi is equal to 0.8. So let's do phi is equal to 0.8. Okay, this is our, again, this we can optimize over this one as well. So now the coefficients for this damped trend is going to be L0, B0, alpha, beta star, and now we have a new coefficient, which is phi. You get the idea. The methodology is pretty much the same. But let me show you something. Here on the left-hand side, the trend component is going to be added linearly. Look at that. It's LT plus HBT. So if h is equal to 1, these are going to be the coefficient of the trend. The coefficients are going to be 1, 2, 3. These are large coefficients, right? We want to get we want to damp this. We want to get, for example, something like 0.8. That's the goal. And then it increases at a decreasing range, right? So it's going to be 1.5 or something like that, right? So this is what we want to do. And this formula is going to enable us to do that, right? So let's look at that. When h is equal to 1, what do we get? You put phi to the power of 1. So there's only one phi. So phi is going to be equal to 0.8. So this is your first coefficient. Again, if you're reading this later on, I'll make it color-coded. So now the coefficient that we're multiplying it by the trend is 0.8 instead of 1. If h is equal to 2, what do we get? We get phi plus phi square, plus phi squared. So 0.8 plus 0.8 to the power of 2. So what do we get? 0.8 plus 0.64 is going to be 1.44, right? So this is 1.44. And if h is equal to 3, I'm going to write it here. So phi plus phi squared plus phi cube. So 0.8 plus 0.8 squared plus 0.8 cube. If you do the math, you will get 1.95. So this is going to be 1.95. As you see, here the phi was large. If I start with a smaller phi, so of course the flattening, the damping is going to be, the coefficients are going to be smaller, right? So here, look at that. So we say, this is the linear version. So on the left, this is the linear version. This is the nonlinear version, right? The damped version. So what is that final value? What is that final value for the coefficient? So the final value, guys, I'm talking about this one. What is that final number that we need to multiply it by the trend? So basically I'm asking, the question is, what if h goes to infinity, right? If h goes to infinity, what do we have? So we have an equation. So basically your multiplier is going to be summation of phi I goes from, let's say, 1 to h, and now I'm sending h to infinity. So there's a formula for that. Basically, phi 1 plus phi, well, let's do phi plus phi squared plus all the way phi to the power of h and sending h to the infinity. So there's a formula for that. So now, as long as phi is between 0 and 1, eventually it will converge to this number, phi divided by 1 minus phi. And in our example, it was 0.8 divided by 1.8. 1 minus 0.8, which is 0.2, so it's 4. So eventually, if h is infinity, well, if h is a large number, if h is, let's say, 1,000, 2,000, so then the multiplication here is going to be 2,000, but here is going to be only 4. So now you're seeing a damping effect. Hopefully that makes sense. All right, now let's move on to the next model. Okay, so now here's just we have already seen something like this a lot before, but again, this is one example from the textbook. We are looking at an Australian population, and population is one of those things that you cannot assume is going to increase in a linear fashion into the infinity. So yeah, so we want to predict it for 2018 to 2032, and then obviously if I use a Holt linear trend method, it's not as realistic as the damped method. Okay. This is just one good example that you can think of. All right, now let's explore the last family of exponential smoothing methods. This is the one with trend and seasonality. Okay, so the method is called Holt Winter, and Holt and Winter, they extended the Holt linear methods to capture seasonality, right? If you follow me with for the very first slide that I told you that, hey, this is the high level picture, just understand this one. Now the rest of the slides should be pretty straightforward, right? So now we are adding the third component, right? That is seasonality. This method comprises basically the forecast equation and three, well, I think we're missing an off here, and three smoothing equation, right? So the smoothing equations, one is going to be for level, one is going to be for trend, and one is going to be for seasonality. So there's going to be more parameters here. Now we have alpha, beta stars, and gamma, right? So this model has, obviously, well, when we get to the equations, I will show you what are the parameters. However, these seasonal components, there are two ways to add it to the method, right? We can add it in an additive fashion or multiplicative way. So we're going to do it additively when the seasonal variations are roughly constant through the time series, right? So if you have something like this, we're going to do additive, right? But if I have, so let's use a right color. Let's use a red here. If I have multiplicative, if the seasonal variations are changing proportional to the level of time series, basically increasing or decreasing, we can, in a linear or nonlinear fashion, we can do multiplicative. So the multiplicative example is like this. Seasonality is small and it's getting bigger as we go further. So for the red time series, we're going to use multiplicative seasonal components. For the blue ones, we're going to do the additive seasonal components. Okay, now let's look into the formulas and smoothing equations for the Holt Winter's additive and multiplicative methods. So I'm going to explain the additive one, and the switching from additive to multiplicative is pretty straightforward. So let me actually highlight it. So this is going to be our forecasting equation, and we're going to have three smoothing equation. So that's why sometimes we call these models or methods triple exponential smoothing methods, right? Because we are looking into three things: level, trend, and seasonality. Okay, so starting from your forecast equation, the one at the top, it's pretty straightforward. We're going to say, your forecast, or it can be predictions as well, right? Because we're going to use the same formula both for calculating the fitted values as well as forecast values, right? So it's a combination of some level and then linear trend. Why we say it's linear? Because we are doing h multiply something. And then this is new. This is a new component. This is a seasonality, right? For now, forget about this thing. Forget about this index t plus h minus m multiply k plus 1. So I'm gonna demystify the next slide. But it's just some sense of seasonality from previous season, right? This m is basically the period of the seasonality. That simply means that if you have a quarterly data, m is equal to 4. If you have monthly data, m is equal to 12, and etc. Right? So the idea is that, well, actually, let's look at an example. This is Australian domestic tourism, and as you can see, this is clearly there is some trend and cycle. So I can look into the trend and cycle like this. So this is one component. Then there's clear seasonality component, and that seasonality, it seems that the magnitude is changing. So we can do multiplicative seasonality, right? So this blue one is going to be our multiplicative seasonality versus the orange one, which is additive seasonality. In this case, the predictions into the futures is not that different, but sometimes it makes a big difference if the magnitude of seasonalities is changing over time, right? All right, so now that we understand what is this forecasting equation, let's focus on our smoothing equation, right? So smoothing equation starting from level. And again, pretty straightforward. It's going to be a weighted average of, what is the level component, the net level component, plus what was the previous prediction, and weighted average. And we are smoothing it by alpha, right? So let me actually show you what I'm saying. So here's an exaggerated data set. And imagine we have a combination of trend and seasonality. And let's say this is a pretty straightforward seasonality, right? And so this is your YT versus t. And I can go ahead and decompose it into its components, right? So we have a trend component. So I'm going to say that imagine these are the fitted values, right? So this is going to be your level plus trend. You can think of it as LT minus 1 plus BT minus 1. Remember, h is equal to 1, so that's why the fitted values are going to be LT minus 1 plus BT minus 1. And then there's another component, which is our seasonal component, right? I try to make it... Again, the seasonality should be regular, so otherwise we call it cycle. So this is this regular seasonality, and this is going to be my S seasonality T minus M. Okay. So again, forget about the indices. I'm gonna fix this time index for you in the next slide. But at the core of it, it's it. We are breaking down this red line into two components. One component is a combination of level and trend. The other one is just seasonality. So this means that if I want to go back and calculate the level components is going to be something like, what was the previous level plus trend? Level plus trend is simply whatever your y is minus seasonality. So if I take this red one, the red line here, and subtract the purple one, I will get the blue one. So this is exactly that part, right? Plus, what was the previous prediction? The previous prediction was, LT minus 1 plus BT minus 1, right? So this is your level component, which makes sense. Then the next one is your trend component. The trend component is pretty much the same, because we're saying that, okay, what's the slope plus a weighted average of the previous prediction for the trend. And so this equation is pretty much the same as the Holt linear trend model. And finally, the last one is your seasonal component. The seasonal component, now we're adding a new variable, gamma and 1 minus gamma. And it's a weighted average between the actual seasonal value plus what was predicted for the previous seasonal time step, right? So this is the additive version, and hopefully it makes sense. And now how we switch from additive to multiplicative. So this is just mathematical operation. We know that if you go from plus to multiplication, your minus signs are going to become, divisions, right? So that's what we have here. So instead of, let me actually use the highlighter. Instead of this, let's do yellow. This plus here, we're going to have multiplication. And then all these minus signs are going to become division. And yeah, the ones that are related to seasonality, right? So for example, you don't touch the trend, right? The trend component is pretty much the same. So this is the net. So again, this is going to become your division, right? And LT minus 1 minus BT minus 1, this is going to be combined together. So this is your blue line here. Let's say this is your blue line. Okay. All right. So the only thing that we haven't explained is what is this? Where is this coming from, right? What is this time index T plus H minus M multiply K plus 1? So in a nutshell, what we're going to, M is clear, right? M is your seasonality period, 12, 4, you name it, right? So what is K? K is is the floor or integer part of this fraction, H minus 1 divided by M. And H is your forecasting horizon. For example, if you're forecasting 12, in this example, let's say this is quarterly, 12 quarters in advance, you're going to subtract 1 and then divide it by 4. So it's going to give you the previous cycle in the last year, right? So it's going to be 11 divided by 4. And the integer part of that is going to be 2, if that makes sense, right? So I can use this notation. The integer part of 11 divided by 4 is going to be 2. So you're going to use, your K is going to be equal to 2 in this example. But again, what are we trying to do? We're saying that, imagine this is a monthly data, right? Let me explain it on a monthly data. It makes more sense. Imagine we have a monthly data, right? And we are in the month of July, right? So you want to make a prediction for next December, let's say 5 months from now, August, September, October, November, December, right? And then what seasonality you're going to look into? Are you going to look into last July or last December? Yes, you will look into last December because you want to predict the next December. So that seasonal component should come from the right seasonal time period. And this is what K is going to help us to get. I'm going to show you a numerical example on the next slide, and hopefully it makes sense. But again, overall, this is how Holt Winter additive versus multiplicative method works. We also call it triple exponential smoothing. Okay, so here's a numerical example that I promised you we are going to cover. Again, the goal is to figure out what right seasonality we should use. If you want to predict what is the value for next July, you have to look at previous July, not previous December or previous May. To do this July to July, February to February. Again, use the right index. So imagine this is our time is equal to 1. So this is T is equal to 1, and 1 is January 2023. Oops, let's see. 2023, right? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So this is going to be our 12, which is December. Then 13 is going to be our January 24. Okay. So imagine your capital letter T is 13. So we are here. This is our very last observation, right? And then you want to forecast 5 months into the future. So my H is equal to 5, right? So basically, this is what you want to say. Y hat, capital letter T, which is 13 plus 5. So you're interested in Y hat 18, right? This Y hat 18 has 3 components. It has level component, it has a trend component, and it has seasonal components. And you want to pick up the right index for seasonal component, right? So first of all, let's find it. So month 18 is going to be, 13, 14, 15, 16, 17, 18. So this is our 18, and 18 is going to be our June 24. Okay. So if you want to get the right components for seasonality, what is the index that you need, time index that you need? Remember, you have to look at the previous June, right? So where is previous June? It's month 6. So 2, 3, 4, 5, 6. This is month 6, and this is June 2023. So we know that the number that we're looking for is 6. How can we get to that number, right? So this is exactly what we need. Again, this has 3 components. It has level components, trend components, and seasonal components, and I'm looking for the right index. I know the answer must be 6, right? So how do we get that? Remember, there was a formula for that. The formula was S of T plus, plus h, and then what do we have? We have minus m multiply, oops, I don't know why it's, okay, multiply k plus 1, and we know that there's a formula for k. K was the integer part or the floor part of our h minus 1 divided by m. Obviously, you don't need to do any of these things manually, but let's look at that. So the integer part of, what is h? 5 minus 1. What is seasonality? 12. So the integer part is going to be 0, so your k is going to be 0. So we have s of t is 13, plus h, 5, minus m, which is 12, and then multiply k plus 1. K is 0 plus 1. So we get into s of 13 plus 5, which is 18, minus 12, which is s6. So this is what we needed. This is the right seasonality that we needed to pick from previous season. Hopefully now these equations makes more sense. Okay, now let's put it all together and look at all these methods that are going to give us point estimates, point forecasts into the future, right? So going back to our very own airline passenger data, and now we can model it, or we can use different smoothing methods to create the point estimates, right? So the blue one is a passenger, SES, as it makes sense. It's going to predict a flat line into the future. I'm going to use my laser, so this is going to be the flat line. Then Holt Linear trend is going to be the green one. It's not appreciating the seasonality. Then the next one is Holt Winter additive, the red one. And then finally, Holt Winter multiplicative. This is the best model, right? I can zoom in. Let me actually zoom in and show you. So when you zoom in, so this is going to be, actually, let me show you something. So because we're going to use pi-caret for the time series regression, so this is going to be your train set. And pi-caret is going to call this holdout period. So holdout period. And then the rest is going to be your unseen data. Okay, so this is the terminology we use in pi-caret, right? So as you can see, our Holt Winter multiplicative is the best one, because if you compare it with the blue line, so these two, they're very good, right? And then the rest is just projections into the future. We cannot report any metrics because we don't know the actuals, right? So in the Python section, I will walk you through different metrics that we have. We can look into R-square, and I will explain why R-square is not the interesting metrics for time series. We will look at RMSE, root mean squared error. We will look at mean absolute error, also mean absolute percentage error. And then there are a couple of other metrics that in pi-caret report. It's mean absolute scaled error and root mean squared scaled error. Now this S stands for scaled. And again, this is nothing fancy. It's going to scale your metrics with respect to naive forecaster. So scale to, let's say, scaled relative to naive forecaster. So basically, if that number is greater than 1, so this means that your model is performing worse than a simple naive benchmark. So imagine if Maze, let's call it Maze, if Maze is equal to 2, so this means that your model is twice worse than naive forecaster. If it is 0.5, it means that it's better than naive forecaster. Again, we don't necessarily look into these ones because sometimes naive forecaster is not a good benchmark. So if I have a data set like this, I am absolutely not interested to see the Maze mean absolute scale error, at least compared to naive forecaster, because naive forecaster for this thing is not a good benchmark. Okay, all right. Okay, our very final method is Holt Winter's damped method, right? So I'm going to show you the multiplicative version here. That's why we're multiplying the seasonality, and everything else is pretty much the same. We have the level components, we have trend component, we have seasonal component. We are damping that trend, and then there's a smoothing equation for L, B, and S. So this is pretty straightforward, and that's actually one of the models that perform the best because it's going to capture everything you need, right? So there are lots of parameters here. We have L0, B0, we have phi, we have alpha, we have beta star, we have gamma, and we have the first seasonality, right? So we can call it S0 or T minus. Oh, this is some seasonality. Let's put it 0, right? So 1, 2, 3, 4, 5, 6, 7. Hopefully I'm not missing anyone. So there are 7 parameters. The identification is pretty much the same as the SES, Holt Linear that we went over the numerical values, but you get the idea. And this is a parent model, so that means that, for example, if y is equal to, I don't know, 1, or if h is equal to 1, or let's see, if y is equal to 1, we get back to the Holt Linear, right? If the seasonality component is 0, we get back to the Holt Linear trend, or if the trend is 0, we get back to SES. So you get the idea. Everything we discussed so far is a subset of this method. Okay. All right. So to sum it up, this is the slide that we started with. We said that at the high level, understand, depending on the data pattern, which method you should use. So this is what I really want you to take away from all this long lecture videos. And yeah, so basically, let's see what else. I think that's pretty much it. And this is all the models, all the methods. And as you can see, let me actually tell you this. These are all point forecasts, right? So we are not seeing any kind of, let's say, confidence intervals around them. And that's what we're going to do in the next lecture video. In the next lecture video, we're going to go from these methods to models, and by making an assumption that the residuals are normally distributed, and then estimate the variance of those residuals, use those estimate numbers to come up with prediction intervals. So that's a plan for next one. Now, last slide, this is a taxonomy of exponential smoothing methods. There are 9 combinations that we can think of. So for trend, let me use blue. So for trend, there are 3 ways we can do it. The N stands for no trend, A, additive trend, additive damped trend. And for seasonal components, let me use another color. For seasonal component, we can have N, no seasonality, additive, add the seasonality in an additive way or in a multiplicative way. So if you do, it's going to be 3 by 3, so 9 combination. So, and then here's a quick exercise. I want you to pause the video and then give me the name of the method, right? So if there's no trend, no seasonality, what do we get? Yeah, this is your SES. If you get additive seasonality, additive trend and no seasonality, what is this? This is your Holt Linear trend, right? Linear trend, and etc. So if I click, basically these are the answers, right? So for example, if you have something like this is the most, I think, comprehensive model, additive trend and multiplicative seasonality. This is your, and we can add the damped, you see there's this letter D. So Holt Winter's damped method. All right, so that was pretty much it. Hopefully you enjoyed understanding the basics of these exponential smoothing methods. In the next lecture video, we're going to extend them to ETS models. All right, this wraps up our part 1 exponential smoothing methods. In the next theory lecture, I will cover ETS models, and then finally in the lecture number 4, which is part 3, we are going to cover ETS models in Python. Until the next one, take care. If you're looking to stay updated with the latest versions of the course's materials, please make sure to follow my GitHub and remember to refresh your repositories periodically. If you find yourself needing a bit more background in econometrics, machine learning, or deep learning, check out my other YouTube videos for additional insights. And for all the latest news and quick updates, don't forget to follow me on Twitter. Thanks for joining me, and let's keep learning together.